Welcome to Stats with Warnke. This is Chapter 3, Section 2, the least squares regressions. At the top of the page here, you're going to see a few of our vocab terms. So for term number 1, we have regression line. You should be familiar with these from some of your previous math courses, probably like Algebra 1, maybe Algebra 2. It's a line that describes how a response variable, that's our y, that's our vocab term from last section, changes as an explanatory variable. The x also changes. So you might be familiar with these from your calculator. If you go into your TI calculator and you press that stat button and go over to calculate, you'll see a couple different equations. So here at number 4, you'll see linear regression, and then if you scroll down a little bit further, you'll see number 8. You'll also see linear regression. So these actually do the same functions. So if you were to use either of them, you get the same equation. It just flips around the order. We, in statistics, use the y equals a plus bx format. The reason for that is because the a being our constant, the bx is then our linear term, and then we could add on additional variables, so cx squared, dx cubed, etc. And we could continue to add on more and more variables depending on the model that we are using. Since we're just looking at a linear model, we use a plus bx. So that's going to be option number 8 on your calculator. You also will notice that there is a little symbol over top of the y. We read that as the y hat. It's just kind of like that caret symbol. If you were to look at your keyboard, shift number 6 is where you see that at on a normal keyboard. But that hat symbol is our predicted. And when we read that in an equation, we read that as our predicted y value. And that word predicted is super important. As we are going through this section in this whole chapter of chapter number 3, we are using a linear model to predict things, to look at an association between two variables. So you'll see that I've underlined that in several spots here because that is the key word that you use when we are describing things. So in that equation, we have our a term, which is our y-intercept, and our b term, which is our slope. So most often, we're going to use slope to describe things. So that's what you'll notice I have first. So the slope is b, the amount to which y is predicted to change when x increases by 1 unit. So down below in a slightly different font, you will see that I have provided you with a sentence structure. This is a sentence structure that I recommend that you use whenever you are asked to interpret. So you can modify it a little bit, like you don't have to say exactly this, but this is the general format that you need to include. So for every 1 increase in x, so as you're looking at this graph kind of maybe down below, as we move along that x-axis, we go from left to right, so as x increases by 1 unit, y is predicted to increase or decrease. So if the slope is positive, that would increase our y value, or whatever that context is, by that much, or decrease if our slope is negative. For our y-intercept, that third thing down, we have, again, a sentence structure that you can use where that y-intercept, is the predicted y in context when we have no x's, when x is equal to 0. So that is the y-intercept is the predicted value of y when x is equal to 0. So moving on down to that example, you'll see that we have a scatter plot. It also includes a title up top, and it includes a scale with labels for each of those. I always recommend that you include those in your graphs because it makes it a lot more clear what we're looking at. So in this graph, you'll see that we do have a y-intercept, which would be just about right there. The blue line doesn't quite go all the way to 0, but if we were to extend it just a little bit further, it'd be just a little bit below 40,000. And you can see that we actually have our equation here with the variables substituted in. Now this is an important point that I did not talk about yet. So instead of using x and y, we can also include words. So instead of having a normal equation with like a y and a hat symbol, we'll use price with the hat symbol over top. Now, if you choose to use x and y, if you're using that in an equation, if you're writing on your homework or something like that, you will need to define or initialize those variables. You need to say that y is the price of an used F-150. So that's why I always recommend that you include just the words in your equation, because otherwise you're going to need to do that for every single variable that you choose to do. It also gives you the context just so that you can reference that a little bit later. So the first thing that you are asked to do is to describe the scatter plot in context. So whenever you see that phrase describe, the acronym STUD should come to mind. So S, you're looking to describe the strength of this relationship. And what you can also use to describe the strength, or to help you define what that strength is right here they've included the correlation coefficient, that R value for us. That is going to help us know exactly how strong it is. So that 0.81, that's not super strong, but it's not weak by any means. So we're going to classify that as a moderately strong. That's the S in STUD, is the strength. The D then gives us the direction, because that's a negative number. That's going to be the negative direction. For T, that is the type. It's a linear relationship. And looking at the scatter plot, I would say that this looks pretty linear. I don't see any like sort of curve in that data or anything else that would indicate that this was a nonlinear situation. And so we have that there is a moderately strong negative linear association between miles driven and price in dollars of Ford F-150s with no unusual features. So that U is our unusual features. We don't see anything that stands out, any points or anything else like that. So I would describe it with no unusual features. We also include context. So our X context, our explanatory variable, is our miles driven, and our response variable is that price. So it's our STUD plus some context. If we move down to interpreting the slope. So once again, we're looking at our equation. We have our y-intercept right here. So I'm going to label that as the y-int. And then this would be our slope. So up above, you saw that we have some vocabulary that I recommend that you, framework that you use whenever we're describing the slope. So for every one additional x, so for every one additional mile driven, the predicted price of an F-150 will decrease by $0.1629. So be careful with your labels here. We always describe things as predicted because this is just a model. This is not an actual like vehicle that we are describing. This is just a prediction based off of a series of transactions that we have recorded here. So as that number of miles driven increases, the price decreases at a rate of, for every one additional mile, the value loses about 16 cents. So just be careful that if you were using a different label there instead of dollars, that you would include that appropriately. I just recommend that you stick with dollars and use the decimal. For part C, interpret the y-intercept. Again, we can use that sentence structure from up above. So in part 3, we see that we have for A is the predicted, and then y in context for x in context. So we're going to use that structure whenever we're talking about a y-intercept. We're talking about when x is equal to 0. So we have 38,257 is the predicted price of an F-150. So that's our y in context, the predicted price of an F-150. And then our x variable is for 0 miles driven. So that's the structure. You can kind of piece it around just a little bit, but I recommend that you stick to that framework because that's going to give you all of the important terms that you need, all of the important vocabulary terms. And then for D, predict the price of an F-150 that has been driven for 100,000 miles. So we go up to that equation, and we see that miles driven is our x, so we take that 100,000, and that's where we plug that in. We're using that same notation. We do a little bit of computation. We come up with 21,967. So over here, you'll see that in context, the predicted price, again, that predicted word is very important that we use to say that this is a model that describes a general relationship. We're just guessing at what it would actually be. So the price of an F-150 driven for 100,000 miles, we would expect it to be around $21,967. Flipping over to the other side, we have just a couple more vocab terms that are very important that we use when we're talking about these particular models. One of them is extrapolation. So the reason we produce these models is so that we can then use them to make predictions about things. But we have to be careful that we only predict to things that would be appropriate to predict. So we're going to have some scale along that x-axis. We don't want to go well outside of that. It is okay to extend a little bit beyond it. That's part of making models, is we want to make some predictions, but we don't want to go too far beyond it. So if you look back at that graph on the other side, you'll see that it goes up to around a vehicle that was with 150,000 miles, somewhere in that range, 140, 150,000 miles. And so if we wanted to predict a car a little bit beyond that, maybe like 160, 170, that would be well within our ability to say, like, okay, we think this might continue in this linear fashion. But to try to predict a car with like 250 or 300,000, since that is significantly beyond the scope of the cars that we use to make this model, that would be considered extrapolation. When you use that regression line to predict something that is far outside of the interval of values that we used. So be careful when we're trying to, when you're asked to predict or when you're trying to come up with something well outside. A little bit is fine. We have to make models to get those predictions, but to get something way out there, that's a little dangerous. The last thing that we need to talk about then is a residual. A residual is the difference between what we predict and what is actually the case. So in that scatter plot, you saw all those actual car values that they were sold for. And then we want to compare that to our predictions. So it says, find and interpret the residual for a truck that had been driven for 70,000 miles and was sold for 22,000. So we can take that 70,000 miles, plug that back into our equation. So I have that right here. And we ended up with a predicted price of 26,854. A residual is the difference between that observed price and the predicted price. Here is the equation that I recommend that you use. So the easy way to remember it is that because we're in an AP class, you're going to do A minus P. So a residual is the actual amount minus the predicted amount. So we take the actual amount the truck was sold for, 22,000, minus our predicted value of that 26,854, and we end up with a residual of negative 4,854. A negative residual gives us an indication that the predicted value was larger than the actual value. So that would be an overestimate. Whenever you have a negative residual, that means that we tended to overestimate. A positive residual then would be the opposite. That's when our actual value is larger than our predicted, which would mean we had an underestimate. So those are all of the vocab terms that are associated with linear regression for this particular section. I hope that you guys have a wonderful rest of your day.